So where we left off last time was with sort of the state of our understanding of light and matter as of, say, the middle of the, well, really the turn of the century, turn of the 20th century. We by then had a fairly good idea that matter was made out of atoms, even though we didn't maybe have a complete picture of what was going on inside of them. And we had a fairly convincing idea that light was a wave, even though we hadn't quite figured out a wave and what. And that's where we sort of left off last time, was this question of that Young showed with his double slit experiment fairly convincingly that light can both constructively interfere and destructively interfere.
Who was that?
That was Young, and I meant to look up the date of Young's experiment, and I forgot to do that. I want to say it's somewhere around the middle of the 1700s.
With a J, right?
Young.
With a J?
No. Y-O-U-N-G. Not like the psychologist guy. And the fact that light can interfere means that light is a wave. But any model that people had for the medium that was doing the waving seemed unsatisfactory because of sort of the strange properties that that material would have to have. And the idea of the luminiferous ether hung around from the late 1700s to well into the 20th century. You still will read people talking about the ether as late as 1920, 1925. But the idea was so troublesome that it was never a particularly satisfactory explanation for the nature of light. A more satisfactory explanation for the nature of light comes from the work of James Clerk Maxwell. And we're talking about Maxwell, middle of the 1800s, 1850, 1860, well, mid to late, 1860, 1870. And what Maxwell was working on really had nothing to do with light at all, at least not when Maxwell started working on it. Maxwell was concerned with electricity and magnetism. It was concerned with, in particular, exploring the connection between electrical phenomena and magnetic phenomena. And the way that we had begun talking about electricity and magnetism as of the 1800s was in terms of these things called fields. We talked about an electric field, we talked about a magnetic field. The idea of a field is a little bit of a tricky one, and it's fraught with some sort of philosophical issues. So I want to spend a little bit of time at the beginning of today talking about what we mean by a field. The need for the idea of a field comes from the fact that there appear to be certain things that happen in nature across empty space without anything connecting to objects. For example, if we take the Earth and the Moon. The Earth and the Moon exert a gravitational force on one another. Newton figured that out in 1687. But what Newton didn't provide is any sort of mechanism for how that force happens. In other words, what does the Earth do to the Moon 250,000, 225,000 miles away to pull it towards itself, and vice versa? What does it do to this pen to pull it down towards the Earth? The gravitational force is strange in that it seems to operate through empty space. If I drop the pen here, it falls through the Earth. If I drop the pen here, it falls through the Earth, despite the fact that the gravity has to go through the table. How does the gravity do that? What is the thing that's making this fall down? Newton explicitly said that he's not going to make any hypothesis at all about what gravity is. He's only going to say what gravity does, which is it gives a force given by this equation, and that allows you to calculate how big the gravitational force will be. But he doesn't give any why as to why gravity happens. And so this method of exerting a force is called action at a distance. In other words, one object acts on another object through empty space with no physical connection, no physical communication between those two. And that's a little unsatisfactory if you're trying to conduct trying to construct a theory of physics based on physical mechanical interactions between things. The situation is the same with electricity and magnetism. In fact, the equation is the same with electricity and magnetism. If I have a positive charge and a negative charge, the attraction between them is equal to some constant times the charge of one times the charge of the other divided by r squared. Newton's law of gravitation and Coulomb's law of electrical attraction are identical in form. It's the amount of stuff times the amount of stuff divided by the distance squared. Just like there's no mechanism for why two things are gravitationally attracted, there's no mechanism that explained why things were electrically attracted to one another. It was simply an empirical equation that people figured out. This is how much force there is. So as a attempt to give some reality to the force, people came up with the idea of the field. And the way it works is, instead of saying the Earth magically attracts the moon, which is 250,000 miles away, you say what the Earth does is create a gravitational field. And a gravitational field exists in empty space, and it gets weaker as you go out, and I'm going to represent the field as a bunch of little arrows filling up space. And if you put a mass in a gravitational field, that mass experiences an acceleration due to the field. So instead of Earth mysteriously acting on the moon, you have Earth creating a gravitational field, and the moon responding to the presence of that gravitational field. So in some sense, a field is just a mathematical abstraction. It is a set of numbers that describes something that's happening every place in space. And there are two kinds of fields we can talk about. We can talk about a field that's just a number. For example, if I wanted to express the temperature in this room at every point. At every point in this room, there's a temperature, right? 75, 75, 75.1. Up here near the lights, it might be 79. Over by the windows, if it's cooler in the hallway, it might be 70. Back here, behind the fan of the computer, it might be 90 degrees. In the space right in front of your nose, it might be 80 degrees because the air you're breathing out is warmer than the rest of the room. We can imagine putting a little number at every point in this room, floating in space, that describes the temperature of that point. And it would be an infinite amount of numbers, right? Because there's an infinite number of points in this room. So every point would have its own number that describes some quantity, in this case the temperature. That kind of field is called a scalar field. It's just a number. When we look at the weather map in the 6 o'clock news, and they show a map of the United States with a bunch of numbers on it, those numbers represent a sampling of a scalar field, which is the temperature at every point in the United States. Now, they don't give the temperature at every point in the United States because there's not enough room to fit all the numbers. But conceptually, we understand that even though they only show the temperature in New York and Baltimore and Chicago, that there is a temperature in Harrisburg, Pennsylvania, even though they might not show that temperature. So the field exists at every point in space. And it's not a thing. It's just a bunch of numbers describing something, namely the temperature. Okay? There's another kind of field called a vector field. A vector field describes a quantity that has not just a size, but a direction. If we wanted to construct a vector field in this room, we could put a number at every point in this room that describes how fast the air is moving. Okay? Most of the places in the room it would be 0. Okay? Up here by the heating vents, there would be little arrows pointing down, 1 meter per second. Back here behind my computer, there would be little arrows pointing that way because the air is moving that way. Outside of your nose, there would be a little arrow pointing that way, and then that way, and then that way, and then that way, as the air goes this way, in and out, and in and out, and in and out. So we can't just put a number at every point in space. We have to put a little arrow because the quantity we're measuring, the speed of the air, has both a size, how fast it's going, and a direction, which direction the air is going. So when we see a map of for example, wind speed on the evening news that's showing which direction the wind is blowing and how hard in various places. What that is a vector field. It's a little arrow at every point in space, the way I've drawn it here. And of course, this field is three-dimensional, right? This is the Earth. There would be arrows all the way around here and all the way out in space. And I've only drawn a representative sample of them, but it's understood that at every point in space there's an arrow describing how strong the force of gravity would be if you were there. Just like on the weather map, there's a number telling you what the temperature would be if you were there. The difference between the field on the weather map, which describes some other thing, temperature, when we talk about a field in physics, like a gravitational field, or an electric field, or a magnetic field, we treat it as if the field is a real thing. Okay? That is philosophically maybe a little bit suspect and a little bit fuzzy. And when we get into the interpretation of quantum mechanics and start talking about things like electrons as being fields, we'll talk about what that means. But physicists tend to treat a gravitational field or an electric field or a magnetic field as if it is an entity that has a real existence. Now, you can not do that if you like. If you like, you can say, what is real is the force experienced by the moon. The gravitational field is just an abstract mathematical description of how big that force is at various points in space. It's not a thing. Just like the bunch of numbers on the weather map is not a thing. Right? The thing is the temperature, how hot the air is at that point in space. The bunch of numbers is just an abstraction. You can say, what's real here is the force that's experienced by an object. And the field is an abstraction. Or if we change this to electricity, if I have... Well, the one you're probably more familiar with is magnetism, actually. Because almost everybody at some point in either elementary school or middle school does this experiment where they take a bar magnet and they put it under a piece of paper and they sprinkle a bunch of little iron filings on top of it, right? And the iron filings will line up sort of and make a pattern like this. And what we say is that those iron filings are lining up along the magnetic field. Okay, so the magnetic field of this magnet is a bunch of little arrows that point from the North Pole to the South Pole at every point in space, and that arrow shows what direction a magnetic object, like an iron filing, will turn in that magnetic field to line up with it. So you can say that the field is not a thing, the field is just describing the behavior of an object near a magnet. Or you can say the field is the thing to which the magnets are responding. It's a question of the ontological status of a field. So without getting too deeply into philosophy right here, I'm going to talk about an electric field for the time being like it's a thing. An electric field is what electric charges make in space. So to go back to the picture we had of the Earth, if I've got a proton in space, that proton makes an electric field. And if I put an electron in that space, another proton in that space, it will move in the direction that that field points. And if I put an electron in that space, because it has a negative charge, it will move in a direction opposite to the direction that that field points. So what Maxwell was looking at then is the connection between electric fields and magnetic fields, which had been known for quite a while, that electricity and magnetism are not entirely separate phenomena. They're related. And without getting into the mathematics of what Maxwell did, which I could do, which I do in the Einstein class, which takes up a day and fills our head full of arrows and upside-down triangles and things that I don't think we need to bother ourselves with in this class. But just to talk about it in the abstract. There are phenomena that connect electricity to magnetism. I'll give you one example that again, everyone has probably done in middle school. You take a battery, you take some wire, you take a nail or a bolt or a screw, you wrap the wire around it, and you connect it to the battery, and that turns the nail or the bolt or the screw into what? A magnet, right? It makes a little tiny electromagnet. And it's not very strong, but usually you use it to pick up paper clips and stuff. That's the only thing you have in your middle school classroom that's light enough for this magnet to pick up. What this tells us is that electricity can be used to make magnetism. Or that an electric field can somehow be used to create a magnetic field. This is a connection that was known about since, let's say, the middle of the 1700s, although I'm really bad with dates on electromagnetism. But certainly well before Maxwell's time, this phenomenon was known about. The converse phenomenon, which you may or may not have seen, is that if you take a coil of wire with no battery connected to it and connect it up to a current meter, okay, something that measures current or voltage. Let's keep an arrow at 0. And take a magnet, a permanent magnet, like a bar magnet. And take that magnet and place it through the ring of wire. It will make the needle on the voltmeter jump. It will cause electrical current to flow through this wire, to flow around this loop of wire, and cause this needle to read the presence of electrical current. If you just hold the magnet in the circle, it doesn't do anything. Okay? If it's sitting still, then it creates no electricity. But the second you move it, it creates an electrical current. Okay? Which means that a magnetic field by itself doesn't create electrical current, but a changing magnetic field does create an electrical current. And what Maxwell figured out was a relationship, a parallel relationship between electric fields and magnetic fields, which is that a changing electric field, and this is the symbol I'm going to use for electric field, the E for electricity, the vector over top telling us that it's a vector field. A changing electric field creates a magnetic field. Which we write as a B with an arrow over top. One of these days I'm going to research who, where, and when they started using a B for magnetic field, because I don't know why. I know why they don't use M, because M already stands for too many things. It stands for mass, it stands for meter, but I don't know why B was the choice. And like the example with sticking the magnet through a coil of wire, which, by the way, is where electricity comes from. I mean, all the electricity flowing through the wires in this room comes from somewhere in a power plant, a turbine spinning a big magnet in a coil of wire and causing electricity to flow through those wires. A changing magnetic field creates an electric field. Without getting into the mathematics, again, of what Maxwell did, basically, he took the equations that describe this process and the equations that describe this process, And notice that if a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, that a changing electric field would create a what?
Changing magnetic field.
Who's the changing magnetic field?
Yes, but also just if, let's see, a changing electric field creates a magnetic field, and a changing magnetic field will create what? An electric field. So this raised the possibility for Maxwell of an electric field that creates a magnetic field that creates an electric field that creates a magnetic field that creates an electric field. Okay? If we have an electric field that's changing over time, and the way I've drawn it, over space as well, that electric field can create a magnetic field. And the way the equations work out, they're actually perpendicular to one another. Since that changing, so I'll use black for electric. I'll use sort of faded orange for magnetic. Since this magnetic field is also changing, that magnetic field can create an electric field that's changing. And since that electric field is changing, it'll create a magnetic field that's changing. And since that magnetic field is changing, it'll create an electric field. And that electric field will create a magnetic field. And when Maxwell looked at the equations for the relationship between this changing electric field and this changing magnetic field, and how they changed over space and time, what he found was that the variation of the electric field and the variation of the magnetic field had the mathematical shape of a wave. A wave not of stuff, but a wave of electric and magnetic fields. And then what Maxwell did was figure out how fast this wave would propagate itself through empty space, which depends on the properties of electric fields in empty space, and it depends on the properties of magnetic fields in empty space. There's a quantity in the equations for electricity called epsilon naught, which is called the I can never remember which one is permittivity and which one is permeability. I think it's the permittivity of free space. I don't know how to spell permittivity. Permittivity of free space. Which was something that was measured. It's how much electric field you get in empty space with a certain amount of charge. There's a quantity in magnetism called mu0, which is called the magnetic permeability of free space. And again, it's a measured quantity, empirically measured. It's how much magnetic field you get in space for a certain amount of electric current or electric field. And Maxwell calculated that the velocity of this wave would be 1 over the square root of mu0 epsilon 0. Okay? So mu0 and epsilon 0 were empirically measured quantities about electric fields and magnetic fields in empty space. When Maxwell calculated this number, 1 over the square root of mu0 epsilon 0, he got 300,000 kilometers per second. Which is what? I mean, it's the speed of light. Yeah, I think I mentioned that number before, or at least kicked it around. That is exactly the speed of light. Now, Maxwell did not know he was working on a problem that had anything to do with light. He thought he was working on a problem with the connection between electric and magnetic fields. What fell out of that connection was the possibility of a sort of self-perpetuating oscillation in electric and magnetic fields that moves through space at the speed of light. It's a very small conceptual jump to then conclude that that oscillation in electric and magnetic fields is what? Light. That's what light is. This is light. Light, in Maxwell's picture, is a wave of electromagnetism. It's not an oscillation of a substance like luminiferous ether or like air or like water. It's an oscillation in the field that describes electricity and magnetism. So what Maxwell did, semi-unwittingly, is take these three phenomena and unify them into a single overarching theory called electromagnetism. And that we will call, because we are talking about 20th century physics, classical electromagnetism. So remember when I said that the history of physics can be looked at as a series of these moments of unification. Newton unified terrestrial gravity and celestial gravity into, or sort of, I don't even want to phrase it that way, unified terrestrial motions and celestial motions under the umbrella of a single theory of gravity. Maxwell unified electric phenomena, magnetic phenomena, and optical phenomena under a single umbrella of classical electromagnetism. And it's an extremely successful theory. Everything that we know about electricity and magnetism can be basically boiled down into four equations, which are called Maxwell's equations. Maxwell gets a little too much credit for Maxwell's equations because only one of them is an equation invented by him. What he did was basically scrape together everything that was known about electricity and magnetism into a concise form that can be written down in a few lines. And I'm going to screw this up, probably. It'll be equals not 0 I plus 0 epsilon 0 partial E equals minus d. Without worrying about what those equations mean, suffice it to say that there is nothing that we know about electricity and magnetism that we cannot derive from those four equations. When I took the graduate qualifying exam in graduate school, which you take first semester of your second year of grad school, and it's basically an exam that covers all of undergraduate physics and your first year of graduate physics. And the format is something, I guess it's a 16-hour exam, 4 hours the first day, 2 4-hour blocks the second day, and 4 hours the third day. 4 questions in each 4-hour block. So basically an hour. It's basically 16 questions an hour per question. And you're guaranteed 1, probably 2 questions about electricity and magnetism. No matter what the question is, if it's about electricity and magnetism, the first thing you would write down on the top of your sheet of paper is Maxwell's equations. For 2 reasons. 1, you'll get credit for remembering how to write down Maxwell's equations. And 2, there's nothing about electricity and magnetism that if you don't have enough time and are smart enough, you can derive starting from these 4 equations. So they really do encompass everything that we know about electricity and magnetism. And then if you take these equations and combine them, they give you this, which encompasses everything we know about light. So Maxwell's contribution to physics was extremely important, both in sort of setting into stone everything that was known up to his time about electricity and magnetism, and then opening up the doors to a description of light in terms of electric and magnetic fields. What was needed then, next, was to prove that this is in fact what light is. And the way to do that is to see if taking electrical charges and moving them around, making a changing electric field, makes a wave that travels through space. The person who did that was Hertz. And Hertz's experiment is fairly simple. It basically involves running a big electric current through a couple of wires here and making a spark. Okay, a spark is a bunch of electrons moving really fast. That's going to make a changing electric field. That's going to make a changing magnetic field. That's going to make a wave that travels through space. And if you put two wires really close together here, when that wave hits those electrons, it's going to exert a force on them, and it's going to make them jump the gap over here. So Hertz's experiment was basically making a spark on one side of the lab and looking for a spark on the other side of the lab. Okay, so what Hertz did was basically create the first radio transmission. It wasn't much of a radio transmission. It was basically a really loud burst of static, but it was enough to cause a spark to jump over the gap between these two wires over here on the other lab. And as a result, we named the unit of frequency after her. So when we talk about the frequency of a FM radio station, will be 103.9 megahertz, million waves per second. And so the way something like radio works is by moving electrical charges around. Well, this is a couple of things. First of all, it made us aware that light is only one part of a much, much bigger phenomenon. That electromagnetic waves are not the property of some substance. They are oscillations in this electric field that can oscillate at a whole bunch of different frequencies. Okay? From very low frequencies to very high frequencies. And what we perceive as light is only a small portion of that. What we perceive as light, from red to blue and violet, okay, is the visible part of something called an electromagnetic spectrum. And depending on the frequency of this oscillation, how fast the electric fields are varying in space and in time, you can have electromagnetic waves that oscillate more slowly than visible light, such as infrared light, or microwaves, or radio waves. Or you can have light that oscillates much more quickly than visible light, ultraviolet light, and X-rays, or gamma rays. But all of these phenomenon, radio waves, visible light, X-rays, are all aspects of a single phenomenon, which is electromagnetic waves. They're just electromagnetic waves with different frequencies. So low frequency, long wavelength at this end, and high frequency, short wavelength at this end. And basically the frequency determines the energy of the wave. So the waves on this end are more energetic than the waves on this end, right, which is why ultraviolet light will burn you and X-rays will give you cancer, because as you go this way, you're getting to more and more and more energetic waves. And less energetic waves and longer waves as you get down this end. The wavelength of an electromagnetic wave also sort of determines how big of a thing it interacts with. And we think about radio. How does radio work? The way radio works is you have an antenna, okay, which is made of metal and it's full of electrons. And you send some electrical current through that antenna that varies over time, and it causes these electrons to go up and down. Because Maxwell's equations say that a changing electric field Well, a changing electric field and a moving charge creates a changing electric field, creates a magnetic field, creates an electric field, creates a magnetic field. That motion of those electrons will create a wave that goes out in space. And I just draw it like this, but it goes out in 3 dimensions. It goes out in every direction in space. If I have another wire at some other point in space, this electric field will cause the electrons in that wire to move up and down, because electric fields exert forces on electric charges, so that makes those electrons go up and down. And so if the signal you send to this wave, to this antenna, looks like this, then the electromagnetic wave generated in space looks like that. And the motion of the electrons in this antenna will look like that. And you have transmitted the shape of this signal, which can be an audio signal, for example, through space from one antenna to the other. But it's all based on moving charges, creating changing electric fields, which move other charges. When talking about the wavelength of a wave, basically, if you want these electrons to be able to respond to this wave as it goes by, they have to have roughly enough, how do I want to phrase it? The object that they're in has to be around the same size as the wave. If you look at what the wavelength is of radio waves, it's somewhere between 1 meter and 30 meters. If you look at how big a radio antenna is, it's somewhere between 1 meter, like the one on top of your car, or 30 meters, like the one on top of a radio station. If you ask, what kind of waves does your cell phone use? Your cell phone operates on microwaves. The wavelength of a microwave is a few centimeters. Okay? How long is the antenna on your cell phone? It's a few centimeters. The reason your cell phone doesn't have to have a meter-long antenna like your car stereo is because your car stereo is picking up waves that are this big, and your cell phone is picking up waves that are that big. Visible light has a wavelength between, say, 700 and 400 nanometers. A nanometer is a billionth of a meter, 10 to the negative 9. That's about the size of, say, a large protein molecule. And the things in the back of your eye, in your retina, that pick up, that respond to the visible light falling on them, are molecules called opsins, which are big, long protein molecules. So the things that respond to visible light are things that are about 100 nanometers long or so. When you get into ultraviolet light and X-rays, you're talking about light that has a wavelength about the size of an atom. The reason that's not good is because what will respond to an X-ray is something about the size of an atom. And if that atom happens to be an atom in one of your DNA molecules, which responds to this X-ray the same way the radio waves in your, or the electrons in your radio antenna respond to the radio waves, and one of these atoms gets knocked out of place or moved to some place where it shouldn't be, well, then you've just gone and mutated the DNA molecule, and that's not good for you. That can cause cancer and that sort of stuff. So not only is it that you get more energetic as you go up the electromagnetic spectrum to higher and higher frequencies, but you operate on smaller and smaller scales. Okay? So we're talking about meters, centimeters, microns, and nanometers, and smaller as we go up, 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 up. And there's no limit. I mean, you can have radio waves that have a wavelength of 100 miles. You can have cosmic rays that have a wavelength of the size of a proton, 10 to the negative 15th meters, a thousandth of a trillionth of a meter. So you can go as far on either end of the spectrum as you like. But this discovery that moving charges create changing fields that travel through space opens up this whole electromagnetic spectrum to our exploration. And nowadays we use the whole electromagnetic spectrum for various things. We talk about this a lot in the astronomy class because if you're an astronomer, and you're looking at different phenomena that happen in the universe, some of them with very high energies, some of them with very low energies, visible light is not always the best thing to use. So when astronomers talk about telescopes, they're not just talking about the things that you look through. There are radio telescopes with dishes the size of a football field that look at very, very low energy things in the universe. There are microwave telescopes. There are ultraviolet telescopes that have to be launched up into the atmosphere because the atmosphere, into orbit above the atmosphere because the atmosphere blocks ultraviolet light. There are X-ray telescopes and microwave telescopes. So there's information in the whole electromagnetic spectrum that's useful for looking at phenomena that happen at different energies. So with Maxwell's picture of electromagnetism under our belt, we can let go of the idea of the luminiferous ether. We don't need it anymore. We don't need a stuff. We don't need a substance to be the carrier of light anymore. The thing which carries light, the thing which is light, is this electromagnetic field. And again, we can quibble about the realness of the field, but it certainly seems real if it can vary over time, it can oscillate, and it can move charges. So we will treat the electromagnetic field as a real thing, and then it becomes light. It takes a good 50 years or so, though, until people stop talking about ether. What really happens, the way Maxwell thinks about his electromagnetic field, is that somehow underneath the description of the field there has to be a mechanical ether that is what the field is. So Maxwell draws like little things with like little gears and stuff, like trying to figure out how a force can be moved from one point in space to another. He's still looking for a mechanical structure underneath the ether, underneath the field. And so you don't get the ether disappearing entirely until... I have a book by a guy named Sir Oliver Lodge which talks about the ether, and it was written in 1924, 25 or so. So the ether idea takes a long time to die off. But what's eventually realized is if you believe that the field is a real thing, you don't need the ether anymore. That the real thing becomes the field, and it's the oscillations of that field that are light. So, now it's 1910, 1912. We think we know what light is, okay? Oscillations of electromagnetic fields. We think we know what an atom is by Rutherford. Tiny, tiny little positively charged nucleus. Electrons zipping around the outside somehow, like flies in a cathedral. Was Rutherford's analogy. And what we want to do then is construct a mechanical picture of what's happening in an atom. What are those electrons doing? There is a natural analog to describe what's happening in an atom based on what we know about another very similar system. We've got a very heavy object in the center and a bunch of lighter objects moving around it. And that system is what? So the solar system, right? It's a very simple analogy to say, well, the solar system is a big heavy mass in the middle with a bunch of little tiny masses attracted by the force of gravity and therefore held in orbit around it. An atom is a small, heavy, positively charged center with little tiny light objects moving around it in circles, held together by the force of electrical attraction. So the atom then just becomes a electrical solar system with the force of gravity that holds our solar system in check, replaced by the force of electrical attraction. Now there's some features that our solar system has that an atom doesn't have. For example, our solar system is flat. All the planets orbit around like this. There aren't any planets in our solar system that orbit like this. You can say, well, why aren't atoms? Why is that? And And by this time it was understood that that's just an artifact of the way our solar system formed. Because our solar system formed from a big rotating cloud of gas, as that gas cloud collapsed, it flattened, and what you wind up with is everything moving in a circle, in a flat circle. But you could, if you could go out there and push the planets around and fling them around at will, you could make a solar system that looked like this, with planets moving around in all sorts of crazy directions. But because our solar system formed from a single spinning gas cloud, everything goes around in the same direction. So that's not a problem for the analogy. The problem for the analogy comes when you calculate, all right, well, let's do for an atom what Isaac Newton did for the solar system. Isaac Newton said, all right, I know how far away the Earth is from the sun. I know how fast it's moving. I know the force of gravity, so let's calculate its orbit and figure out how those things are related. Let's calculate, for example, how fast an electron would be moving inside of an atom based on the fact that we know the equation for electrical attraction, we know the equation for an object moving in an orbit, and so let's do just a quick estimate of how fast an electron would have to be orbiting in an atom to be held in a circular orbit by the force of electrical attraction. We know that atoms are about somewhere between an angstrom and a nanometer across. An angstrom is 10 to the negative 10th meters. A nanometer is 10 to the negative 9th meters. Everybody knows, I hope, scientific notation enough to know what these mean. This is telling you how many decimal points you move over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 9 zeros and then a 1. So it's 1/10,000,000th of a meter is an angstrom. And a nanometer is a billion. Let's imagine an atom as, let's take a hydrogen atom, the simplest atom, 1 proton, 1 electron. Let's imagine it as an electron in orbit around a proton with a radius of half an angstrom, give or take. The exact numbers are not terribly important. We're just going to do a ballpark estimate. The force on that electron is given by Coulomb's law, which says it's some constant times the charge of the electron times the charge of the proton divided by the distance squared. The charge of an electron and a proton are the same. Okay? The elementary charge is 1.6 times 10 to the negative 19th coulombs. Coulomb is the guy that figured out the law for electrical attraction, so he's the guy that gets the unit for electrical charge named after him. So that's a number that's known. K, this constant, which is 1 over 4 pi epsilon 0, which is that weird little number I talked about before, is again a number that's just been measured. It's around 9 times 10 to the 9th Newton meters squared per Coulomb squared. It is a measurement of the strength of the electric field. It's the analog of the G in Newton's law of universal gravitation. So we can calculate the force between an electron and a proton that are half an angstrom apart. Let's do it. Okay, so the force is equal to K Q times Q divided by R squared. K is 9 times 10 to the 9th. Q is 1.6 times 10 to the negative 19th. That squared is going to be 1.5 times 1.5. It's going to be around 2. And 10 to the negative 19th times 10 to the negative 19th is 10 to the negative, is that 38? 19 and 19? Yeah. divided by r squared. R is half an angstrom, so that's 0.5 times 10 to the negative 10th. That squared is going to be a quarter times 10 to the negative 20th. So let's see. Let's because we're not concerned with the exact number, because I'm just ballparking it, I'm going to not pull out my calculator here. 2 divided by a quarter is 8. 9 times 10 to the 9 is basically 10 to the 10th. You round 10 up to 9. Sorry, 9 up to 10. Negative 38 over negative 20 this is going to be 8 times 10 to the negative 18th. Subtract the exponents and divide. So 10 to the 10th times 8 times 10 to the negative 18th is 8 times 10 to the negative 8 newtons of force. So that's the force between the electron and the proton and an atom, 8 times 10 to the negative 8 newtons. Now you might not have a good feel for how big or small that number is. A newton is the amount of force necessary to basically to hold up a amount of force necessary to hold up a liter of water is 10 newtons. So this is about a billionth of that. Which seems like a pretty small force, but when you're talking about the force on a single electron, it's actually a pretty big force, because these two things are so close together, because this number down here is so small.
You mean to hold up against gravity?
Yeah, to hold up against the Earth's gravity, yeah. This doesn't give us anything, though, that we have a feel for in terms of a normal number. What I want to now calculate is, if this thing is in a circular orbit experiencing that much force, how fast will it be going? Newton recognized the relationship between how fast something is going and, for circular motion. What force is required to make something move in a circle at a particular speed? We call that for centripetal force. And the equation for centripetal force is that force equals mv squared over r. When something is with a mass m is moving in a circle, the force necessary to keep it moving in that circle at a particular velocity is given by mv squared over r. And this is just something that if you had taken the foundations of physics course before this one, you would recognize that equation. It's just one of the basic equations of Newtonian physics. Which means v equals square root of the force times r divided by m. Did I do that right? F m r square root. Yeah. So if I want to calculate the velocity of an electron experiencing this force in a circular orbit, then that's the square root of the force, which we just calculated was 8 times 10 to the negative 8 newtons, times r, which was half an angstrom, 0.5 times 10 to the negative 10th meters, divided by the mass of an electron. If you look up the mass of the electron, which I forgot to do this morning, what you find is that it's a very small number. 9 times 10 to the negative 31 kilograms. Okay, which is a very, very small number. 9 times 10 to the negative 31. Okay? Again, let's be lazy and not use our calculators. 9 times 10 to the negative 31 is basically 10 to the negative 30. since 9 is almost 10. A half times 8 is 4. So this is negative 18 in the numerator, negative 30 in the denominator, so that makes 10 to the negative 12. Okay? 18, sorry, not negative 12, 12. 18, negative 18 plus 30 is 12. Square root of 4 times 10 to the 12 is 2 times 10 to the 6. And because this is a velocity, the units for that are going to be meters per second. 2 million meters per second. So if an electron is like a planet in a little solar system, the speed with which it has to move to stay bound in that orbit is 2 million meters per second. Well, if you do it without all the crazy rounding off I did, it's actually 1.59. So we did pretty good with our screwed up math. It's 1,590,000 meters per second. If you like that in miles per hour, it's 3.5 million miles per hour. That seems a little fast. At least in everyday terms, 3.5 million miles an hour seems pretty fast. It's faster than anything we know about in the world around us. But if we treat an electron like a little planet, and we treat the electrical force like an analog of the gravitational force, and we assume that an electron obeys the same classical laws of motion that a planet does, what we find out is that in order for an atom to be in a stable orbit around a proton, given the size that we know an atom is, it has to be going 3.5 million miles per hour. And maybe that's true. So every atom is a bunch of electrons zipping around at 3 million miles an hour. Well, there's a problem with that picture. Remember I said that based on what Maxwell tells us about light, that light is an electromagnetic wave caused by moving electric charges. And if we take a radio antenna and we move the electrons up and down in that radio antenna, they give off an electromagnetic wave. If an atom has an electron in it that's doing this 3.5 million miles per hour, that electron should give off what? It should give off an electromagnetic wave. It should create an electric field, a magnetic field, and it should radiate light. What kind of light? Is it X-rays? Is it radio waves? I don't know what kind of light. We could figure out its frequency. If it's going 3.5 million miles per hour, how long would it take it to go around once? If this is 2 pi times an angstrom. So this is about 6 angstroms around once. Distance equals velocity times time. Time equals distance over velocity equals 6 times 10 to the negative 10th angstroms. That's how far it is. Sorry, 10 to the negative 10th meters. That's how far it is to go around the atom once. Divided by the speed, which is about 2 times 10 to the 6th meters per second. So this is 6 times 10 to the negative 16th. 3 times 10 to the negative 16th seconds. So that is 10 to the negative 12th is trillionth. So that's a 10th of a quadrillionth of a second per orbit, which means this should be giving off radiation with a frequency of something like 10 to the 16 waves per second. Which is 1,000 terahertz. I'm trying to figure out where in the electromagnetic spectrum that is. I don't have the electromagnetic spectrum in my head in terms of frequency very well. Well, I can figure it out in terms of wavelength, so give me 1 second. C equals lambda nu, lambda equals nu over equals C over nu equals 3 times 10 to the 8 meters per second divided by, what did I say, 10 to the 16th? So that's 10 to the negative 8 meters, which is about a nanometer. So this was going to be ultraviolet light. If the electron is moving around that fast, it goes around in a tenth of a quadrillionth of a second, it's going to be giving off ultraviolet light. Don't worry about the steps I went through to calculate that. We will learn how to do that in about 2 weeks. Which means that every hydrogen atom, when it's just sitting there, should be spewing out ultraviolet light. That would be bad news for all of us right now, since our bodies are 90% water, each of which has 2 hydrogen atoms in it. You would have to wear sunblock from the inside to escape from the ultraviolet radiation of all your hydrogen atoms. But it wouldn't last for very long, because as the electron emitted that radiation, it would lose energy. Right? That law of conservation of energy says when you emit energy, energy has to be lost somewhere. What would happen is that the electron would lose energy, and I don't remember this exact calculation, but it's no more than a dozen orbits or so. It would plummet into the nucleus, and it would stick there. Okay? And what you'd have instead is a proton and electron stuck together. The electron would radiate away all of its energy via ultraviolet light. That's not the way the world works. If that's the way the world works, every hydrogen atom in the universe would have collapsed into a proton and electron stuck together billions of years ago. Hydrogen atoms are stable. They last, as far as we can tell, forever. Every hydrogen atom in the universe today has been here since the Big Bang 13.5 billion years ago. So an electron doesn't radiate away all of its energy in a trillionth of a second and spiral into the nucleus and crash there. But that's what it seems like classical physics and classical electromagnetism taken together, Newton's theory of objects moving in circles and Maxwell's theory of what electrical charges do when they're moving, if you take those things and combine them, you get this bizarre catastrophic model of the atom that can't possibly be what's really happening. This is the first hint that classical physics is not going to be adequate to describe whatever it is that electrons and atoms are doing. That somehow classical mechanics plus classical electromagnetism gives us a failed model of the atom. The planetary model of the atom does not work, at least not if we calculate the behavior of the electron according to strict classical Newtonian physics. An electron cannot be doing the same thing that the Earth is doing around the sun. If it were doing that at 1% the speed of light, it would be radiating out huge amounts of electromagnetic energy all the time, and all of its kinetic energy would be used up in a fraction of a second. This is the problem facing us in 1915, 1920. And it's a problem of incompatibility. And that's always the problem facing physics. And it's when scientific revolutions happen. When one of our theories seems to be in conflict with another one of our theories. Or when two theories which seem to work perfectly well in their own realms, classical physics which describes balls rolling down ramps and planets and cannons and all that stuff that that Newton and Galileo used it for. And classical electromagnetism, which describes what happens in wires and what happens in magnets and what happens in light. If we apply these two sets of tools to try to ask what's happening inside of an atom, what we get is nonsense. What we get is a picture of an atom which cannot correspond to reality. So there's a disconnect here. And the idea, the presumption, when there's a disconnect like that, when you take two perfectly good theories and apply them to a single problem and get nonsense, the presumption is that there's something wrong with one or both of those theories, that one or both of them need to be fixed, or that we're just simply thinking about the problem in the wrong way. We have to rethink our model, because the model of the planetary atom is not adequate. So what do we do? How do we approach this question? Well, the way to approach it is to look at what atoms really do. We know that a hydrogen atom doesn't spew out a constant stream of ultraviolet light, but what does a hydrogen atom do? Or any atom, for that matter. So the question is, what is the real relationship between light and atoms? What do they really do? We need more data. We need to understand empirically the interaction between light and matter in a very, very precise way if we're going to figure out why our model doesn't work. So the phenomenon that we're occupying physicists at the beginning of the 20th century, from say 1900 to 1920, 1925, were phenomenon related to the emission and the absorption of light by matter. That question had not been addressed yet. Light and matter were treated as separate things. Maxwell's equations describe light perfectly well when it's light, but don't address the question of what happens to that light when it hits something and is absorbed by it, for instance. So the question then becomes, what does light do? Or what does matter do when it's emitting light? And there had been some observations floating around for quite a while that suggest that something different is happening than classical physics might suggest. We're going to do this experiment ourselves in a couple of weeks, hopefully. I hesitate to plug this in here, but we'll see how it goes. What I have here is a high voltage power supply. By high voltage, I mean input 120 volts, output 5,000 volts. So this is a 5,000 volt transformer, basically, that steps the 120 volt current that comes out of the wall to 5,000 volts between the cathode and the anode. And when it says danger, high voltage, do not put fingers into sockets, they mean it. 5,000 volts is, 500 volts will snap your arm back, but 5,000 volts is like break out the defibrillator. So you got to be careful with these things. And what I have here is a couple of tubes filled with gas. Okay, you can't see it because it's all transparent gas, but it's an evacuated glass tube, each with a different kind of gas in them. Hopefully, these things are notoriously wonky in terms of how well they work, but there we go. Anybody care to guess what gas is in that tube? Yeah, neon. This is the familiar neon gas color that we recognize from a neon sign. And if we're interested in explaining what an atom, say a neon atom, does when it gives off light, what we have to do is look at that light more closely and sort of figure out what wavelength it is, what frequency it is, why it's whatever brightness it is. One way to do that is to take that light and separate it out into a rainbow or a spectrum. You can do that a bunch of different ways. You can run it through a prism and look at it through a prism. You can run it through a piece of plastic with a lot of lines carved on it, called a diffraction grating. You can reflect it off of a piece of plastic with a lot of lines carved on it. One thing that works really well is a CD, and I don't think I have a CD with me in my bag anywhere. But if you hold a CD up next to this, you can see this red light spread out into a rainbow. Now, we're used to seeing light spread out into a rainbow from something like the sun, which is made up of a bunch of different gases at a bunch of different temperatures, and it's very dense, and the atoms and molecules are colliding with each other a lot, and that's why the sun is opaque. You can't see through the sun. The sun is, despite being a gas, it's incredibly dense, and it gives off a complete spectrum of light. You get something very different when you look at a single gas that is very low density. In other words, the material is transparent. The atoms do not collide with each other that often because there's a lot of empty space in between them. If you look at the spectrum of a neon, what the hell is that up there? Yeah, if you look at the spectrum of a neon light, if you spread that light out into a quote-unquote rainbow, what you get is something that looks like that. It is not just a particular frequency of red light. It is not just red light. What you get is lots of lines, each of which corresponds to a particular color or a particular frequency. So in this case, we're going from red, yellow, green, blue on this end. Lots and lots of red lines, but also a very strong yellow line in the spectrum, and some green lines that we don't really see when we look at all of this light together because the red dominates. But the color of that light is unique to neon. And this thing heats up. I can't take it off right now. I was going to switch it with another tube, but I have to wait for it to cool down. Every atom in the periodic table, it turns out, will produce a sort of signature. This one's broken. Will produce a signature set of what are called spectral lines. In other words, every element in the periodic table, if I swap this out for hydrogen or helium or krypton or mercury, I would get a different sort of fingerprint of that element. This was discovered, when did Fraunhofer discover the solar spectrum? I want to say it was something like 1880. What are the chances I remember how to spell Fraunhofer? Luckily someone remembers how to spell Fraunhofer. It's a beautiful spectrum of the sun, which shows, in this case, not just emission lines, but absorption lines, which we'll talk about. Well, will we talk about today? I guess we'll talk about today also. This is the spectrum of the sun. The sun's light spread out into a rainbow, but it's spread out so far that we've stacked it on top of each other. So really, this would be one long thing from red, and then yellow, and then orange and blue. It would wrap around the whole room 4 or 5 times. But they've taken it and they've cut it into slices and stacked it up. So it goes from red up to blue here. And what we see is, and this was discovered by Fraunhofer, and what I meant to do was look up the date, but sometime in the late 1800s, that the sun's light on top of the rainbow are these lines that are dark in the solar spectrum. And you know, some of them are very narrow, some of them are very wide, and one at a time, we were able to associate each of these spectral lines with a particular element. I'm going to go back to neon for a second.
Wasn't Tesla the first person to use neon?
He may have been, yeah. I don't know. I'm not one of those Tesla files, so I don't know as much about Tesla as I maybe should. So here's an example of hydrogen, mercury, neon, showing the spectrum that you would get if I stuck a hydrogen tube in here. Okay, I would get a spectrum that looked like that. If I took a mercury vapor tube, I would get this. Mercury is actually very interesting because you see it has blue, it has, well, sort of in between green, yellow, orange, red. Mercury vapor, because it has lines in every part of the spectrum, actually produces a very white light. And a lot of the street lights, halogen street lights, have mercury vapor in them because mercury vapor has a red line and a yellow line and a blue line and a green line. And when you look at a mercury light, it looks white.
So all like vacuum tube lights that they use in shops and stuff have like at least a drop of mercury in them to make them white?
Yeah, I think so. And then, again, the mercury vapor is particularly good because it's
Is that just to increase luminosity? Or?
well, yeah. I mean, we'll talk about in a couple weeks. We'll talk about fluorescent lights, how they work. It's actually a combination of the spectrum like this and it's called a black body spectrum, which we'll talk about next week. And what we can actually, when we get the spectroscopes and do the lab, we can actually look at the neon light, the fluorescent lights in the lab and see what those look like. The spectrum at the bottom is what you get. This is what you get if you take hydrogen and you put it in a tube and you run 5,000 volts through it and make it shine. Okay, you get spectral lines that are the particular atomic fingerprint of hydrogen. This bottom spectrum is what you get if you took hydrogen and took a tube of hydrogen and shined a full rainbow of white light through it and looked at the light that comes through the other side. And what you would find is that certain frequencies of light get absorbed by the hydrogen. Okay? As that white light shines through the hydrogen, that hydrogen gas absorbs this frequency, and this frequency, and this frequency, and this frequency. And if you look at the two and compare them, the frequency that hydrogen absorbs when you shine white light through it is the same frequency that hydrogen emits when you heat it up and cause it to emit light. So the emission spectrum and the absorption spectrum are always sort of mirror images of one another, or photonegatives of one another. Right? The frequencies that hydrogen emits are the same as the frequencies that hydrogen absorbs, and the frequencies that mercury emits, and the frequencies that mercury absorbs, and so on. This was first and foremost a valuable tool for science. And the science of spectroscopy, in other words, looking at spectra and separating that light out into its component wavelengths and figuring out which wavelengths come from which atoms, gives us a way to identify chemical elements from a long way away, just by looking at light. So, for example, the reason we know... it's getting harder and harder to give examples now because we keep exploring different places in the solar system. The reason we know that Saturn's atmosphere is hydrogen and ammonia and methane is because we look at light reflected from Saturn and we look at where Saturn's atmosphere absorbs light, and we know what frequencies are absorbed by what elements here in the lab, so we can say, oh, that's a ammonia absorption line, and that's a methane absorption line, and that's a hydrogen absorption line. So it's an incredibly valuable tool for astronomers that don't have the luxury of being able to actually touch the thing that they're studying. The fact that we can identify chemical elements from light years away is what makes astronomy, is what makes at least identification in astronomy possible. In fact, the element helium, we don't have helium here, the element helium in the periodic table, which is number 2, okay? Hydrogen's here, helium's here in the top corners of the periodic table. The word helium comes from, what's the root of the word helium? Anybody know? Helios, which means what? Sun. Why is the element helium named after the sun? Well, the sun is largely helium. Well, the sun is about, sun is about 75% hydrogen, 25% helium. How did we know to name the element helium? You know what I mean? I mean, yeah, the sun's 25% helium. How did we know to call it helium? Yeah.
Floats.
True. It does float. The fact that it floats is why we never discovered it on the Earth. Helium was discovered on the sun through spectroscopy before it was discovered on the Earth. helium was identified as an element whose spectral lines we don't recognize from anything we've ever seen here on Earth, that exists on the sun. So it was named after the sun, sunium. This is the element that exists on the sun that we haven't managed to find here on Earth. And then when we went looking for it, we found a little bit in the atmosphere. There's not much helium in the atmosphere because it goes up for the most part. And it's hard to find because it's not chemically reactive, right? Helium's in that last column of the periodic table called the noble gases, and it doesn't really form chemical compounds, so it doesn't show up in any chemistry experiments, really. So helium was actually discovered via spectroscopy on the sun before it was identified in the Earth's atmosphere. So spectroscopy is a valuable tool, but at this point in time, in terms of understanding it, a complete mystery. There is no reason we can think of why a particular atom would only give off particular colors of light and not any other color of light. So the mechanism that needs explaining now in 1900 to 1920 is a fairly complicated relationship between atomic structure, and clearly there's something different about a hydrogen atom and a mercury atom and a neon atom in terms of how many electrons they have and where those electrons are and what those electrons are doing. And if we remember chemistry class, there's all this business about electron shells and stuff like that. But there must be some kind of relationship between the structure, say hydrogen, helium, carbon, and the light given off by those atoms. So the puzzle then for physicists at the beginning of the 20th century is figuring out a model that explains not only what electrons are doing inside of an atom, but what is it about the structure of an atom that causes hydrogen or helium or carbon to give off not just any old light, but very specific frequencies, very specific wavelengths of light. There's nothing in classical electromagnetism that would suggest why only one wavelength would be given off by an electron and not some other wavelength. Because all that determines the wavelength is how fast the electron is going. There's nothing in classical physics that says an electron can go whatever speed it wants. So what we're going to talk about next time are the earliest attempts to reconcile this picture of classical electromagnetism, where light is just a wave caused by a moving charge, and the results of atomic spectroscopy and our study of matter and light, which shows that the way matter emits light is not as a continuous rainbow, but as a discrete set of specific frequencies. Okay. So that's where we will wind up next time. You probably shouldn't read too much further in diamine. I would catch up to where I told you last time, right before the section on, well, into the chapter on radiant energy, but not to the section on Planck and Einstein yet. And we'll start talking about Planck and Einstein, I guess, next time. And we will be back on schedule. Before we go, let me mention the problem packet, which I just realized yesterday that I have not posted to Blackboard yet. So I'm going to post that either right after class or I will post it tonight, depending on whether I decide whether or not it needs any editing or not. I'm only going to post the first third of the problem packet. The problem packet includes, well, no, I can't do that because there's some good stuff in the glossary. I'll post the whole problem packet, and then I'll post the first third as a separate file. The beginning has not only some algebra practice problems to sort of make you aware of where your algebra skills are. You don't have to do those and hand those in. It says in the packet that those aren't for collection. Those are just for your sort of personal use. But there's also some things about guidelines for writing up the problems and things like that. I will also try to really shortly post a sample solution. In other words, what should a well-written up solution to this kind of homework problem look like to help you out while solving the problems. We haven't done any math yet that will, or any problems yet that will help you solve any of these problems, but it's coming. As of next week or so, we'll start to get a little quantitative when we start exploring the Bohr model and the atom. So soon it will be time to start looking at the problem packet and figuring out what problems we can solve. So I'll post that up again, either right after class or tonight, 6 o'clock, 8 o'clock tonight. And it's something you should probably print out and keep with you and take a peek at every so often to see if there's any, we've learned any new techniques in class that will help you solve some of those problems. Okay, so I'm going to end a little bit early today because I don't want to get into the quantum mechanics until next week.